So to analyze data when there are dependent samples, you will need to start by entering two lists of paired data, and then you need to compute a list of differences. So the directions for how to do that are here for StatCrunch, although there is a paired test that we can use that will compute those for us when we actually run the test. But those steps are here. But on the calculator, if we were going to enter those, again, we would first push stat1, and we would enter the data into L1 and L2. And then we would use the arrow keys to highlight L3, and then we would type L1 minus L2 by pushing second function 1 minus second function 2. And then as soon as we hit enter, we see that the calculator will automatically compute. So it took 9 minus 5 and got 4, 10 minus 8 got 2, and 5 minus 2 and got 3. Okay, so in this section, we're going to, when we analyze and run the hypothesis test in the confidence interval, it will be done on list 3 and not L1 and L2. So L3 will now have all of your computed differences. Now the most common error that happens with students when they're using this on their calculator is they will get this error data type, and that just means that you did not have your cursor all the way above this line, so highlighting L3, before you typed L1 minus L2. Okay, so your cursor needs to be all the way above the line here. It can't be sitting in this first position in the list or you'll get this error message. Alright, so these next two pages again are just reference pages to come back to. So a hypothesis test for a paired t-test is actually just going to be a t-test like we ran in the last unit on just that difference unit. So before starting, you would need to enter two lists of paired data and compute the list of differences. So we would go back to the previous page for that. Okay, our parameters, since we're dealing with quantitative data, we're going to have mu1 and mu2. And then the corresponding random variables from our sample data of x bar 1 and x bar 2. We're going to state our null and alternative hypothesis and the level of significance for that second step. And for this one, we do get a new symbol in this section, mu sub d, which is the mean of all the differences. So d stands for differences. So in this case, these are backwards. This should say mu1 minus mu2. So if we take mu1 minus mu2, okay, that will give us the mean of all of the differences between those two populations. And so in this case, our two-tailed test is going to say that mu sub d differs from 0. A left-tailed test is going to say mu sub d is less than 0. And a right-tailed test is going to say that mu sub d is greater than 0. Again, we've got some assumptions to check. So the first of those in this class is always going to be, we're just going to assume a simple random sample has been taken. In this case, our second condition, we need to make sure that the samples that we've taken are dependent or paired samples. And then the next condition is we need a normal population of differences, or at least 30 pairs of data with no outliers in the differences. Okay, so in this case, we were going to, again, using the techniques from Chapter 6 to assess normality, but this gets done on, if it's in the calculator, on list 3, okay, on that list of differences. Okay. And then our last condition here is that the population standard deviation is not known for each group, which is almost always the case. So if those conditions are met, we can run the paired t-test. And our test statistic for that one, again, our new statistic here instead of x bar is going to be d bar. Okay, so this is the average of the differences, which if we did this by hand, we would add up all the numbers in the difference list and divide by little n. But that's going to be next to x bar on the output screen when we run the test. Okay, S sub d, so the standard deviation of those differences, is also on that output screen, and it's next to S sub x. Because your calculator doesn't know if you've given it values of x or values of d. So when we run this t-test, that output screen, every place we see an x, we're going to replace it with a d for differences. So our test statistic in this section is going to be that observed value of d bar minus mu sub d, which in this section, or for this course, that mu sub d is always going to be 0. And then we're going to divide by s sub d over root little n. Okay, so in this class, again, mu sub d will always be 0. And then we're going to obtain the p-value. using technology, and we'll make a graph to make some sense out of that p-value and the value of d bar and t. And then making a decision about HO, same logic as before. We're going to reject HO if the p-value is less than or equal to alpha and fail to if it's greater. And then stating a conclusion, same logic as always. If we reject HO, there is significant evidence to conclude HA. And if we fail to reject HO, then there's not significant evidence to conclude HA. And again, the last page for reference in this section before we look at an actual example. So again, for confidence intervals, again, we're still using the acronym PANIC. So again, the parameters still the same as what we just had. Assumptions all the same as what we just had. But in this case now we're going to run the test or the procedure called paired t-interval to get a confidence interval for that difference. Again, the I in PANIC is for the interval estimate, but we start with our point estimate, which for this one was going to be d bar. Again, that's going to be on the output screen next to x bar. And then we're going to compute a confidence interval for mu d by using the t-interval on that list of differences. So next to list here, that is wherever that list of differences is. Which typically for us, we're going to be putting that into L3. Okay. And then the confidence level here we've got is 0.95 is going to be a typical one, but again, we'll get that from the problem. But on the output screen here, we have our confidence interval for mu sub d. This x bar is really d bar, which is a point estimate for mu sub d. And this value that says s sub x is actually s sub d when we go to look at the formulas. Okay. And again, we can also use StatCrunch to get these values. And again, our lower limit and upper limit for that confidence interval are displayed here. So again, our conclusion is going to, again, depend on if both of those endpoints are positive. We're going to be C% confident that the mean measurement of all objects in group 2 exceeds the mean measurement of all the objects in group 1 by some amount in that interval. And if they're both negative, we're C% confident that the mean measurement of all objects in group, these should be group 1 and 2, those are also backwards. Group 1 is less than the mean measurement of all objects in group 2 by an amount between that upper endpoint and lower endpoint, where again I've written absolute values here to remind you to remove the negatives, because that's already taken care of in this word less than. But if one of those endpoints is negative and one endpoint is positive, then we don't have any evidence of a difference between those groups.